Today's class. Last time we have talked about silicon oxynitride, right? On page 276. We can also call it oxynitride. Okay, so both silicon oxynitride or oxynitride are fine. Okay, we use SiON for oxynitride. But sometimes because we don't know the composition of oxygen and the nitrogen, therefore, sometimes we also use SiOXNY for oxynitride. Okay? That is, oxynitride consists of two components. One is silicon dioxide, right, oxide. And the other is nitride, silicon nitride. And also, so we have oxynitride. So oxynitride means two words, oxide and nitride, right? So oxide and nitride becomes oxynitride. Okay, for the dielectric constant, because dielectric constant is very important for dielectrics, what is the relative dielectric constant for silicon dioxide? 3.9. Good. Okay. So Robin is well prepared for the final. Okay. Okay. So K is 3.9 for SiO2. Then how about for nitride? 7.8, good. So K is equal to 7.8. Then how about the question is, how about for oxynitride? Because oxynitride consists of oxide and nitride, right? So the composition, because we don't know the composition of oxygen and the nitrogen, so two extreme values, when x is equal to 2, y is equal to 0, so that's SiO2. So the K value is equal to 3.9. And the other extreme value is when y is equal to 2, x is equal to 0. That becomes nitride. So the dielectric constant is 7.8 because they are not equal to 0, right? So the combination of dielectric constant must be between 3.9 and 7.8, right? Depending on the composition of x and y. So this changes. Okay. Any questions so far? Okay, as we talked about before, since the value of K is greater than 3.9, so this dielectric we call high K dielectric, one of the high K dielectrics. High K dielectric. If the dielectric constant is less than 3.9, then the material, we call it low K dielectrics. These two are different. For high K dielectrics, what's the main purpose? Maybe Minchen. what is the purpose for us to use high-K dielectrics? To improve CMOS performance. Yes, correct. Then what do you mean by performance? Transistor performance? ID set, okay. Good. So you still remember. So for the purpose for high-K dielectric is used for transistors. For transistors means for from end of line. From end of line. For from end of line, the main purpose is to make transistors, CMOS transistors. That means transistors, MOSFETs. Especially for on current or ID set in microelectronics courses. Okay, so on current. So to improve on current, then what is on current? So on current is equal to ID set. Saturation drain current. That's the most important transistor performance, device performance. That is the formula for ID set. So from this formula, we can see ion, therefore ion is proportional to Cox. Transistor, that's the oxide capacitance of MOSFETs. Okay, so ion is proportional to Cox, and the Cox is also proportional to dielectric constant. Okay, for dielectric constant, and so dielectric constant is equal to. So sometimes we use kappa or K for relative dielectric constant. So from this equation, we can see if we use high-K dielectrics, for example, oxynitride, so the value of K increases. So we can increase, for this one, increases. Ion increases. For on current, we want the on current as large as possible, right? Which means the speed of the transistor or the IC is faster. Okay? Any questions? Okay. If you don't have question, then I have a question for you. The question is, since the dielectric constant for nitride is greater than oxynitride, right? Because we want to increase the dielectric constant, the value of K, in order to improve the device performance. Then the question is, why don't we simply use nitride instead of oxynitride for gate dielectrics of CMOS. Why? Okay. Basically, there are two reasons. The first one, I think I talked about the first reason last time, the end of last class. Because nitride cannot be deposited directly on top of silicon substrate, okay? Let me write it down. Silicon nitride cannot be deposited directly on top of silicon substrate. Why? Because of stress and the thermal expansion coefficient. Issues. Okay. Let's take a look here. For CMOS, let me use NMOS for example. For NMOS, the substrate is P-type. So P-type silicon is silicon, right? And that's the poly gate. That's the gate dielectrics. And also we have spacer. LDD and source drain, right? I believe you still remember. Okay. So for the gate dielectrics, we cannot use nitride because the difference of thermal expansion coefficient between nitride and the silicon is significant, right? And also the stress of nitride is very big compared to silicon. Therefore, the surface of the silicon will be damaged, which means the interface becomes worse if we use nitride directly on top of the silicon, right? That's one reason, the most important reason. Therefore, for the IC process, nitride cannot be directly touched with silicon, okay? And the second reason is nitride can only be formed through CVD. Nitride can Okay, for CVD, chemical vapor deposition. So if, for example, if we compare these two transistors, for this one, if the dielectric constant is nitride, for this one, if the dielectric is oxide, let me compare these two transistors. For the dielectric SiO2, what process do we use for this material? CVD or oxidation? Which one? Who wants? Oxidation. Good. For oxide, we can use either oxidation or deposition. We have two choices, but which one is better? Much better, actually. Oxidation is much better than deposition for the interface of dielectric and the silicon substrate, right? So for this material, the process we use is through oxidation. But for nitride, the process we use is deposition, CVD. So the interface is not good. Interface is not good for deposition. But because for CMOS, the interface is very important. It's very important. Therefore, we prefer oxidation. Okay, not deposition. But for nitride, if we want nitride to be the gate dielectric, the process we use is through deposition. Okay? So because of these two reasons, nitride cannot be used directly on top of the silicon substrate. Okay? Any questions so far? Okay. If there's no questions, then let's move on. Please turn to page 276. There are three important points. The first one, nitride concentration in oxynitride increases. Then the dielectric constant K increases or decreases. Increases or decreases? Okay, Nina. Increases, good. Can you tell us why? Higher dielectric constant than oxide. Good. Yes. Okay, so from here, because for nitride, it has a larger dielectric constant than oxide. Therefore, if we increase the nitrogen concentration, means Y, the value of Y is larger, right? Okay, therefore the dielectric constant increases. So from we have just said, if we want to increase the dielectric constant to improve the device performance, what can we do? Maybe we want to increase the concentration of nitrogen in the oxynitride film. Okay, so we can increase dielectric constant. Okay, and the second point is the nitrogen at the interface. Okay, nitrogen at the dielectric. Let me write at the oxynitride dielectrics and the silicon substrate interface. It's beneficial Okay. The nitrogen concentration at the dielectric and the silicon substrate interface is good. It's beneficial to the device performance. And also to hard carrier effect. What does this mean? For the device performance, means what we have just talked about. Because on current increases, that's one of the most important device performance. Then the other is hard carrier effect. Nitrogen concentration is also good for hard carrier effect. Okay, what is hard carrier effect? That's on page 505. We say hard carrier effect or hard carrier ejection. Again, let me use an NMOS, for example. When the NMOS is turned on, so the gate voltage is greater than threshold voltage, right? And we have electrons from source to the drain. Because the gate voltage is greater than threshold voltage, then the channel is on, channel is formed. So electrons can move from source terminal to drain terminal. Okay? So we have drain current. Okay, that's the material covered in microelectronics. So we are not going to go through details. Okay. So when electrons move from source to the drain, the energy is very big, especially around this area, around drain area. For the silicon substrate, let me use, okay. Okay. For silicon here, because we may have hydrogen bonding, silicon and the hydrogen bonding, because the bonding energy for between silicon and the hydrogen is not so strong. Therefore, because the electron energy, when the electron energy is big, then the bonds will be broken. When the bonds are broken, then it looks like this. Once the bond is broken, then we have the so-called dangling bond, right? And the hydrogen ion. And the hydrogen ion is positively charged. And this hydrogen ion may diffuse into dielectrics. Once hydrogen ion diffuse into dielectrics film, then we have several problems. One is, do you remember oxide charge, right? So this ion becomes oxide charge trapped in the oxide, in the dielectric. So we'll be trapped inside the dielectrics. If we have oxide charge, then the threshold voltage also changes. Okay? So this is not good. But if we have nitrogen at the interface, then this can be improved. Why? Because if we have nitrogen at the interface, it means the bonds here may be silicon and the nitrogen bonds, not hydrogen. The bonding energy for this bond, the bonding energy is around 3.17 electron volts. For this bonding energy, it's about 2.6 electron volts. This energy is much bigger than this energy here, right? So it's stronger. Because the energy is stronger, so it's harder to be broken. Okay? Any questions for this? And this effect we call hard carrier effect. Why hard carrier? Because carrier means electrons or holes. Why hard? Because the carriers are with high energy. They are not really hot, okay? Hot means energetic, high energy. And this effect we call hard carrier effect. And also can be called hard carrier injection. I means injection. Because hydrogen ions or maybe carriers, electrons or holes can be injected into dielectrics. Therefore, the effect can also be called hard carrier injection. Okay? We don't want hard carrier effect happens because the threshold voltage of the device also changes. It becomes unstable, right? In the most of the time, for example, our cell phone or notebook, it becomes slower. Why? One of the reasons is hard carrier effect, because electrons or holes are injected into the dielectrics. Therefore, the threshold voltage becomes larger. When the threshold voltage becomes larger, right? So from this equation, ion decreases. So your cell phones or notebook or computers, the speed becomes slower. Okay? That's probably caused by hard carrier effect. Okay? Any questions? Actually, this concept is kind of important. Okay? Okay, if you don't have any question, then let's go to page 277. Since we know silicon oxynitride is important, then the next question is, how can we form the oxynitride? How to form the oxynitride? Basically, there are three ways or three approaches. Okay, page 277 on your textbook. The question is, how to form oxynitride? Three approaches. The first one is through CVD, chemical vapor deposition. For example, okay, that's one approach. And the second approach is, okay, let me write down. Oxidation of silicon nitride. And the third one is nitridation of silicon dioxide. Okay. For the first one, through CVD, we can use silane and nitrous oxide. The product is oxynitride. Okay, and the byproduct is nitrogen and hydrogen. Okay. Okay, let me explain the chemical reaction a little bit. For nitrous oxide will be first decomposed into nitric oxide and nitrogen. Okay? That's the intermediate step. And then nitric oxide reacts with silane. Okay? So for nitrous oxide, it's decomposed into nitric oxide and the nitrogen. And the nitric oxide then reacts with silane. So we have oxynitride. So we have silicon, hydrogen, and nitrogen. But we don't know the composition of oxygen and the nitrogen. So sometimes we can put X and the Y. Okay. And okay, so and also we have hydrogen. That's the product. That's the byproduct. Vapor gas. And also we have nitrogen here. That's also one of the byproducts. So we can get oxynitride through CVD. Okay, so it looks like this. We have silicon substrate. Then we use CVD, so we have silane gas and nitrous oxide gas. So we can deposit oxynitride on top of the silicon substrate. Okay? And the second one is we form silicon nitride and through oxidation to get oxynitride, which, okay, we can use the plot here. So we have silicon substrate, and then we CVD deposit nitride. And then, okay, once we get nitride, the next step is to oxidize the film, which means oxidation process. So we use oxidation process to oxidize silicon nitride. Okay, for oxidation, what can we do? There are two ways for oxidation at least. Do you remember, 词汇? Oxidation is different from deposition. Okay, for oxidation, two popular methods. One is dry oxidation, and the other is wet oxidation, right? And the dry oxidation is better than wet oxidation. Okay, so for oxidation, we can use either dry oxidation or wet oxidation or steam oxidation. So we can use, for example, oxygen gas to oxidize the film. Then we can get oxynitride. That's the second approach. Okay, and the last one is we form silicon oxide first. So we form silicon dioxide, okay? How can we form silicon dioxide on top of silicon substrate? 子薇 not deposit again, okay? Oxidation. For oxidation, thermal oxidation is different from deposition, okay? For deposition, CVD, the reactants are of vapor phase. So we use silane, which is a vapor, a gas, and the nitrous oxide also a gas, right? That's for CVD. But for oxidation, the reactants are silicon, and for example here, if we use dry oxidation, then we use oxygen. So they can react to form SiO2 on top of silicon substrate, okay? So let's form SiO2 first, and then nitridation. So we can nitridation. For example, we use ammonia gas for the nitridation process, okay? Then we can also get oxynitride as the gate dielectric films. Okay? So basically there are 3 approaches. Any questions? Questions? No? Okay. If you don't have question, let me ask you a question. Okay? Among the 3 approaches, okay, for the first one, is this a good way for us to form oxynitride? Or Yuchen, is this good? Is this a good process for us to form oxynitride on top of silicon substrate? Not. Why? You are correct. This is not a good approach. Why? Because the interface is worse than oxidation, right? Deposition, because we use deposition process to form oxynitride, which is deposited on top of the silicon substrate. So the interface is not good. That will be an issue, okay? So this is not good. How about for the second approach? Yes or no? Okay or not? During the CMOS process, okay, I've mentioned this several times. Okay, one more time, so you have to remember. Okay, during the whole CMOS process, nitride cannot be touched directly with silicon because of the stress and the thermal expansion coefficient difference between nitride and the silicon. Okay, so for this one, we have to form silicon nitride and then oxidize the film to get oxynitride, right? But when we deposit nitride, then it's not good because we will have, because the interface will be damaged. Okay? So this approach is not good either. So what we can do, the best way is to form oxide and then have the nitridation process. For nitridation, we have to use gases containing nitrogen to form oxynitride. Okay? So for nitridation, actually, there are 3 kinds of gases we can use. Okay, so this approach is the approach we can use. But how to do the nitridation? Actually, for nitridation, we can use the following 3 gases. The first one is ammonia. That's the first one. And the second one is nitrous oxide. See? Because for here, then maybe we can guess nitrous oxide can be one of the candidates. So nitrous oxide. And the third one is nitric oxide. Right? Because for nitrous oxide, it is decomposed into nitric oxide and the nitrogen. And the nitric oxide will react with silane. So therefore, the idea is we can also use nitric oxide for nitridation. Okay, because time is up, let's take a break.